we all have some notions of random variables, and when we have studied these random variables, naturally couple of things comes very naturally, like PMF if the random variable is a discrete distribution, or probability density function, or PDF if the random variable is absolutely continuous random variable. So, another thing that comes very naturally, we actually all know, which is known as expectation. Now, we already know that x n, or rather x, which is a random variable, is nothing but a measurable function defined on a probability space. So, if I stick to this definition, and if we think of integral of this measurable function with respect to a measure, in this case let us consider it as probability measure, then, or rather the distribution function, then we can easily define or the integral, and this integral is nothing but we actually know this integral as expectation. So, this expectation of a random variable, which can be viewed as nothing but an integral of a measurable function, is extremely important. And again one can think of higher order moments, like, so expectation is a first order raw moment one can think, which is expectation of x, and if we consider expectation of x to the power r, we can define rth order moment. So, the question is how to define in a nice way, obviously mathematical way, this expectation. Then again there are some interesting inequalities concerning these moments of different orders. We can define these inequalities, we can express the inequalities in terms of general measurable functions, or again naturally, since random variables are all measurable functions, we can again express this in terms of random variables also. So, these moments, and there are some important inequalities related to these moments that we are going to discuss today. Moments and inequalities. So, we are going to discuss some inequalities and some moments, but before that let us do a quick recap. If x is any random variable, we can define x plus. If you recall properly that we have defined this x plus and x minus in the same line as f plus and f minus, that means when we have a function f, which is a measurable of course, and we have defined f plus and f minus. Similarly, exactly similarly, in the same line we define x plus as maximum of x 0, which is x if x greater than equals to 0, and 0 if x less than 0, and x minus, which is the negative part of x, which is maximum of minus x 0, that means equals to minus x if x less than 0, and 0 if x greater than equals to 0. So, this x plus is known as positive part of x, and x minus is known as negative part of x. Therefore, we can immediately write mod x as x plus plus x minus. So, by the definition you see this x plus and x minus both are positive. So, mod x is nothing but x plus plus x minus, and x, the original random variable, can be written in terms of these two variables, which is x plus minus x minus. It has already been discussed, and also it is true that x plus and x minus, they are all measurable functions. So, x plus, x minus, mod x, they are all measurable functions, that means random variables we can think. And the definition of the integral, which is more general definition compared to the definition that we have already proposed in terms of simple functions and non-negative measurable functions. So, here f is any measurable function, and we define integral of f d mu equals to integral of f plus d mu minus integral of f minus d mu. Remember that integral of f plus d mu is defined only for a non-negative function, which is f plus. Integral of f minus d mu is again defined for a non-negative function, which in this case is f minus, and we define integral of any general measurable function in terms of the positive part and the negative part, there is integral of positive part and integral of negative part, and it is just the difference between of these two. Now, remember this integral we can define as long as this is not of the form infinity minus infinity, and as previously if this thing happens, then we say that the integral does not exist. So, whenever we talk about integral, there is always a question whether the integral exists or it does not exist. So, we have to be very careful about first ensuring whether the integral exists or not. Now, this f is a general measurable function. Now, we know that x, that is a random variable, is also a measurable function defined on a probability space. So, expectation of x we can define as integral of x d mu over a, which is integral over a x plus d mu minus integral over a x minus d mu, which we denote by expectation of x plus minus expectation of x minus. So, it is clear that this expectation is nothing but the integral, and since integral can be defined in terms of simple function, if we go back to the basic definition of integral, it is defined in terms of simple functions. So, naturally this gives us an idea or intuition that we can define expectation in terms of simple functions. Let us consider two interesting examples before formally define this expectation, or rather historically introducing the definition of expectation that is due to Kolmogorov. So, let us first consider two very interesting examples, because I have already mentioned that whenever we have an integral, the question of whether the integral exists or not exists should be checked. Now, this expectation is nothing but the integral with respect to mu. So, naturally there must be a question that whether whenever we talk about expectation of x or expectation of any random variable, whether that expectation really exists or not. Now, if the expectation does not exist, that means this should be, the integral should be of the form infinity minus infinity. So, let us consider two interesting examples, one for discrete random variable, another for continuous random variable. So, first one, the discrete variable, that is, let x take the values 0, plus minus 1, plus minus 2 and so on, with probability x equals to k, which is exactly equals to probability x equals to minus k, that is kind of symmetric, which is equals to 3 by pi square into k square, k equals to 1, 2 and so on, and probability, and let us take probability x equals to 0 as 0. Then if we calculate expectation of x plus, this is nothing but summation k equals to 1 to infinity 3 k by pi square k square. So, 3 by pi square is a constant, we can take this outside the summation sign, and this is equals to 3 by pi square into summation k equals to 1 to infinity 1 by k. Now, this sum of this sequence or the series is equals to infinity, that we know from the analysis class that this is equals to infinity. Again, if we calculate expectation of minus x minus, we see that this is exactly equals to infinity. So, expectation of x equals to, as we defined earlier, expectation of x plus minus expectation of x minus, which is equals to infinity minus infinity, and hence we say that expectation does not exist. Similarly, if we consider a Cauchy random variable with PDF f x equals to 1 by pi 1 by 1 plus x square, as x lies between minus infinity and infinity, if we calculate expectation of x plus, which is integral 0 to infinity x by pi into 1 plus x square dx, this is, it can be shown that this is equals to infinity, which is nothing but exactly equals to expectation of x minus, that is equals to integration minus infinity to 0 x by pi into 1 plus x square dx, and hence again here also expectation of x is of the form infinity minus infinity. That means we say that expectation does not exist. That means for a random variable, it is not necessary that expectation will exist. There are some situations where expectation may not exist, and these are two nice examples where expectation may not exist. Now, let us go to the Kolmogorov's definition of expectation. Let us omega script f and p be a probability space and x be a measurable function. There is a random variable we can think. Then the definition is, if probability x equals to infinity is greater than 0 and x greater than equals to 0, then we define expectation of x as equals to infinity. If probability x less than infinity equals to 1 and x greater than equals to 0, that means initially we are going to define expectation only for non-negative random variable x. Then we define expectation of x, which is a limit as n goes to infinity, limit of summation k equals to 1 to infinity k by 2 to the power n into probability that x lies between x is greater than k by 2 to the power n, but less than equals to k plus 1 by 2 to the power n. In general, so this is the definition of expectation due to Kolmogorov, and if you look at this definition, it has some similarity, some intuitive similarity with the simple functions that we have already defined. So, in general, we say expectation of exists if either expectation of x plus less than infinity or expectation of x minus less than infinity, maybe both or maybe both, and then define expectation of x equals to expectation of x plus minus expectation of x minus. So, in one we have defined expectation for a non-negative random variable, and we know that x minus as well as x plus both are non-negative random variables. So, expectation of x plus and expectation of x minus we can define as in one, and then use them to define expectation of any random variable, and obviously we have to be very careful about the existence of this expectation. Now, we discussed a few very important inequalities. One is known as Holder's inequality. It says that if p and q are two non-negative extended real numbers such that 1 by p plus 1 by q equals to 1, and if f is a function that belongs to Lp and if g is a function that belongs to Lq, then fg belongs to L1 and norm of fg 1 of order 1 is less than equals to that, which is equals to integration modulus of fg d mu, which is less than equals to pth norm of f into qth norm of g. Now, the pth norm or norm of order p is defined as norm of order p of f equals to integral of mod f to the power p d mu whole to the power 1 by p. This equality holds if and only for some non-zero constants alpha and beta. We have alpha into modulus of f to the power p equals to beta into modulus of g to the power q almost everywhere. Now, one small remark is that if p equals to q equals to 2, this gives us the famous Cauchy-Schwarz inequality. And again you see this is given in terms of integrals, we can easily convert into in terms of expectations. So, we can get the Cauchy-Schwarz inequality, the standard form which is given in terms of expectation. So, let us prove this Holder's inequality. For p equals to 1 and q equals to infinity, the proof is obvious, but for general proof we have to state one lemma, because we need to use this lemma. It says that if alpha and beta are two non-negative real numbers and for lambda lies between 0 and 1, we have alpha to the power lambda into beta to the power 1 minus lambda. This is less than equals to lambda alpha into 1 minus lambda beta, that is the convex combination of alpha and beta, and equality will hold if alpha equals to beta. So, we will use this lemma in order to prove Holder's inequality. So, let us first take alpha in the lemma. Alpha equals to mod fx to the power p by norm of p of order p raised to the power p, and again beta equals to mod g to the power q, which is norm q to the power q divided by norm g of order q to the power q. Take lambda equals to 1 by p, so that 1 minus lambda equals to 1 by q. And then if we just apply this lemma, we see that alpha to the power lambda and beta to the power 1 minus lambda, we will immediately see that this left hand side is equals to modulus of product of modulus of fx into gx, fx and modulus of gx divided by norm of f of order p into norm of g of order q, which is less than equals to lambda times alpha, which is given as this, plus 1 minus lambda times this. Now, remember this denominator is basically a constant if we integrate it. So, if we integrate both sides of this equation 1, what we get is integral of this entire quantity modulus of f x into modulus of g x by product of norm of f of order p and norm of g of order q d mu less than equals to lambda into integral of this quantity plus 1 minus lambda into integral of modulus of g to the power q by norm of g of order q raised to the power q with respect to mu. Now, please look at carefully this and all the expressions in the left hand side and right hand side, and you will see that the denominator will come outside the integral sign. So, this means that 1 by product of these two norms into integration modulus of product of f and g d mu less than equals to lambda, because this integral modulus of f to the power p by norm of f order p raised to the power p is with respect to d mu is nothing but 1, because denominator comes outside and what is left is nothing but pth power of norm of f of order p. So, the right hand side is exactly equals to 1, and if we just shift the denominator in the left hand side to the right hand side, we will get the Holder's inequality, hence the proof. So, the proof is very simple, just use the lemma, and for a particular choice of alpha and beta, the proof is immediate. Note one small remark that Holder's inequality is trivial when pth norm of f is equals to 0 or qth norm of g equals to 0, because in this case f equals to 0 almost everywhere or g equals to 0 almost everywhere. Now, from this inequality we move on to another important inequality, which is known as Minkowski's inequality, which is a direct application of Holder's inequality. Suppose f and g are in LP, so naturally this implies that f plus g will also be in LP, and norm of f plus g of order p is less than equals to norm of f of order p plus norm of g of order p. That means norm of sum of functions is less than equals to sum of the norms. As we know, or that is we can write in terms of integrals, which is nothing but the definition of pth order norm of order p. So, how to prove this? Before proving, one interesting thing we can note that this looks like this is very similar to the triangle inequality that we know in our analysis class. So, we can say that this is nothing but a triangle inequality in LP space, and consequently this norm of order p can be treated as a norm, and hence this can be treated as a distance function in explaining this inequality, triangle inequality in LP. So, we can define a triangle inequality in LP space as well as a distance function. So, this is a very interesting feature of, or rather the direct consequence of Minkowski's inequality, and a nice interpretation of this Minkowski's inequality. Now, the proof. Case p equals to 1 follows directly from integration of modulus of f plus g d mu is less than equals to integration of modulus of f d mu plus integration of modulus of g d mu. It's a very simple thing to observe. And define now to prove the case situation when p equals to infinity, we define m, capital M, as essential supremum, which is S sub of f omega defined as infimum of m such that mu of omega such that f omega greater than equals to m and mu of this entire quantity equals to 0. We call this norm of order infinity, infinite norm. And this again follows from the result that essential supremum of f plus g is less than equals to essential supremum of f plus essential supremum of g, and the proof follows directly, which is nothing but the infinity norm of f plus g less than equals to the sum of their norms. Now, the non-trivial thing, that is when 1 less than p less than infinity, this is very simple, we have to do just some manipulation and we will get the proof. So, this is integral f plus g whole to the power p d mu less than equals to, we can write f plus g whole to the power p minus 1 into modulus of f d mu plus integral f plus g whole to the power p minus 1 modulus of g d mu, because we just write this in term as modulus of f plus g whole to the power p minus 1 into modulus of f plus g, which is less than equals to modulus of f plus modulus of g. Let us call it 1. Then just apply Holder's inequality to the first term in the right hand side, we get norm of f order p, which is equals to qth order norm of modulus of f plus g whole to the power p minus 1 with q equals to p by p minus 1, because we know that in Holder's inequality there is a condition 1 by p plus 1 by q equals to 1, and from there we can immediately get q equals to p by p minus 1. Again apply Holder's inequality to the second term in equation 1, we will get exactly the same type of inequality as in the second line. Now from 1, consider the left hand side of 1, which is integral mod of f plus g to the power p d mu, which is less than equals to, if we add the right hand side, or that is the sum of the two right hand sides after application of Holder's inequality, this gives us norm of f of order p, norm g of order p into integration modulus of f plus g whole to the power p minus 1 into q into d mu whole to the power 1 by q, which when simplified gives us integration modulus of f plus g to the power p d mu whole to the power p minus 1 by p, because we can put q equals to p by p minus 1. Now you see, in the left hand side we have integral of mod of f plus g to the power p d mu. In the right hand side also we have the same term, integral mod of f plus g to the power p d mu, but raised to the power p minus 1 by p. So let us take the extreme right term to the left and do a little bit of simplification. We will immediately get integration of f plus g whole to the power p d mu whole to the power 1 by p, that is the norm of f plus g of order p is less than equal, which is equals to this norm, which is less than equals to norm of f of order p plus norm of g of order p. So this is a nice proof to see that the same thing, same expression that we get in case of triangular inequality based on real numbers, we get in the LP space, that is norm or the pth order norm of sum of two functions is less than equals to sum of the norms of two functions. And remember, this p is very general, p can start from 1 to infinity. So this is a very general inequality, and also Holder's inequality is also a very general inequality, and we will see immense application of both these inequalities later in probability theory, in statistics, and in many areas. We already have the idea of simple functions and how you have defined integration using these simple functions. So just to go one step further, Kolmogorov, the famous probabilist, actually proposed or provides the definition, a concrete mathematical definition of expectations using using the idea very similar to that of simple function. So and from here we already proved, we have seen that we have proved two important inequalities. One is Holder's inequality, another is Minkowski's inequality. Now again, another interesting thing is that Holder's inequality reduces to the famous Cauchy-Schwarz inequality as a special case. So Holder's inequality is a very general inequality using the some higher order moments, or rather pth order moments. There is I should not say higher order, but some general order moments, and this p can be any number, any positive number. Again, Minkowski's inequality, we have seen that it just follows from Holder's inequality with a little bit of algebra, and again this is extremely important in developing or deriving or getting many results in the area of probability theory. And rather even in statistics, mathematical statistics, many theorems actually have been proved using these inequalities, mainly Holder's inequality or Cauchy-Schwarz inequality or Minkowski's inequality or some combination of them. So these inequalities really play a very important role in the areas of statistics as well as probability.